Hi there, young scientists and engineers. It is I, one of your science teachers, and in this video, we're going to look into what's known as the Doppler effect. The Doppler effect, the one and only Doppler effect. I'd like to start by telling you that that nifty device there on your screens, JBL Flip 6, if I'm not mistaken, I bought that with my Chinese New Year Lycée money. Okay, the quality is very good. Sound fidelity is very good. The range is actually quite good, and don't really use it outside except on this occasion, right? It usually is on my bedroom floor. Okay, and I stream my music through it, and it's very pleasurable to listen to. JBL is not going to pay me, right? If I say it's good, but it's a good product, and I think I got my money's worth for that. But anyway, I got into thinking with this gadget, with this device, because the music that we listen to really are sound waves, right? If you remember, sound waves are, well, they are not just any kind of wave, right? They are not transverse waves; they are longitudinal waves, longitudinal waves. And when we say longitudinal waves, if you remember, the oscillations are parallel to the direction of travel, right? So uh, if let's try to visualize, right? How the sound waves spread from a speaker. So here's my speaker, S, sound source speaker, SSS, and the sound waves would be like concentric circles, right? Coming from that speaker. That's right, concentric circles. The centers are coinciding. All right, there you go. You get the picture, right? And those lines that you see, those are actually crests. Those are actually the maxima, right? So let's see if we can visualize it in another way, right? Here we go. Or something like that. Minima, maxima, minima, oh, maxima, minima, maxima, minima, maxima, minima, maxima, minima. Okay, you got a picture, right? And the distance between those lines, I don't know if you remember this, that's known as the wavelength, right? The distance between two consecutive maximas. Their wavelengths. Now, these sound waves, they spread equally, evenly in all directions. That's right, all directions. Right? And that's why if you were here, you'd still hear the sound just as loud as if, well, you might just be here and hear the same quality, same loudness of sound. Yeah. Okay. Now, over the that's where my Chinese New Year money went, at least some of it. And here's a visualization of how the sound spreads. Right, the sound spreads from a source that is not moving. The source is not moving. Another way to say this is stationary. Stationary. Okay, now, this is not the stationary that we buy in the WIS PTA. This stationary means not moving. Okay, over the weekend, I was in Admiralty, and I was in this nice place. Okay, I was meeting up with someone. I was waiting for her, and I was having a meal in advance, and I was looking out over at Queensway, right, a semi-busy thoroughfare. And on a Saturday afternoon in Hong Kong, I found it quite strange. I saw an ambulance or sort of fire truck. I think it's a fire truck, right? That's why I have the picture there. Okay, an ambulance or a fire truck, right, with its siren on, right? And I'm supposed to give you the link, right, to a video that you can watch. Okay, but I observed, right, a couple of changes with the sound of that siren as the fire truck moved closer to me in my location, and then as the fire truck moved away from me, right, away from my location. Right, so I'd like to summarize what I heard using a new slide. I have to remove all of those. Okay, here we go. One of the things I noticed was that the sound intensity, right, the loudness changed. The loudness or the intensity changed. Loudness or volume? I'm not so happy with loudness. It's not so cumbersome, right? Volume. But when I say volume, it does not mean, remember, it does not mean it's the space taken up. It's not that one. Okay, it's how loud the sound is. Okay, it has to change. Okay, how did it change? Well, as the fire truck moved closer to me, moved towards me, I'm the observer. The intensity actually, hey, that's right, you guessed it. The intensity actually increased, right? The sound became louder. Now, in the same way, as the fire truck moved away from me, moved away from me, the observer, the intensity decreased. Okay, it's not as loud anymore. It became softer, right? Sound. Okay, so here's one thing that we observed. Okay, in that restaurant, right? The sound of the waves, the sound waves, changed, became louder as the source was moving towards me, and became not louder, became softer as the source moved away from me. The other thing that changed is actually pitch. Yeah, pitch. And when you click on the link that your teacher is going to send you, uh, you can have a look at this in your set for yourself, right? So the loudness and the pitch was changing. Okay, so how did the pitch change? Well, the pitch changed in this way. The pitch actually increased. It increased as the object moved towards you. Move towards observer. And decreased, okay, as this fire truck, I believe, moved away from me, away from the observer. Okay, move away from the observer. Okay, and this perceived, right? The perceived. So we believe it to be, we sense it to be, we think it is changing, but actually it's not, right? The perceived change in frequency of waves could be sound waves, could be light waves, okay, as the source of what? Well, the source of these waves, okay, moves relative, so that's moving towards or away, moves relative to an observer, okay, perceived change in frequency of waves as the source moves relative to an observer. This is known as the one and only Doppler, right, effect. I think it was Christian Doppler. I can't remember. Maybe he was Austrian, and he uh, he did some work on sound. Hey, I believe he did some work on sound. I might be wrong. And to this day, right, this effect named after him. Okay. Do you remember the sound waves from the speaker when the source is not moving? Let's have a look at that again, but this time when the source is moving, right? Because that's where the Doppler effect. That's what the Doppler effect is about. Okay, next slide. There we go. Oh, what is this? Right, the source is not moving. That is my source not moving. Remember, we have concentric circles. Ta-da! And the distances between these circles is the wavelength. Now, you will observe that the wavelength does not change. That's right. Okay, so stationary source. Okay. Now, what's the picture look like? What's it like when the source is moving? Okay, well, we have the source here. Now remember, the observer is here. The sound waves actually look like this. Yeah, that's right. Oop, did I do a good job on that one? Maybe not so good. All right, that's much better. Okay. Let's do one more. Okay. That's a source. Here's my observer, right? The wavelength closer to the observer appears to be smaller or shorter, whilst those away from the observer look to be longer. So we're moving towards the observer. Right? The observer will observe lambda to be shorter if the source is moving towards that observer. Moving away from the observer, the lambda appears to be longer. Okay, shorter if it's moving towards the observer. The source is moving towards the observer. Okay, now I don't know if you remember, the speed of a wave is the product of the frequency of that wave multiplied by its wavelength. Now, because the medium is not changing, the speed is not changing. Okay, so this source of waves is not moving from glass to air, from a liquid to glass. No, it's in the same medium. It's in air, right? That siren is traveling in air. It's not moving from air to liquid. So it's traveling the same medium. So the speed is not changing. Ah, okay. This is the wavelength, and this is the, hey, you guessed it, the frequency. Frequency. Okay. Now, if the if the speed is not changing, so C is F lambda, this is not changing. If lambda is big, then the frequency is low. So on this part, not only do we observe the lambda or the wavelengths to be longer, but the frequency we observe to be lower. Now, conversely, because C is F lambda and C is not changing, on this end, right, the part moving towards the observer, the lambda is actually short. And that's going to make the frequency high. And high, right? So the observer, right, observes a frequency or a higher frequency when the source is moving towards the observer. And when the observer, well, when the source is moving away from the observer, the frequency is perceived to be lower. Let's summarize that, right? Next slide. Okay. Oh, we still got these. Delete. Delete. Okay. Moving toward observer. Oh, sorry. Let's do this instead. Am I doing that right? Actually, why do we do that? Okay, moving towards observer. Is it towards observer? Okay, the lambda is perceived to be shorter, and the frequency, right, higher. On the other hand, moving away from observer, the lambda is observed to be longer, and the frequency is lower. Right? Moving towards the observer, once again, the wavelength appears to be shorter and the frequency higher, right? Higher frequency means high pitch, right? High pitch. This is known, right? A shortening of the wavelength, okay, a perceived shortening of a wavelength is known as a blue shift. When the source moves away from the observer, the wavelength increases perceived to increase, and the frequency decreases, lower pitch, right? Lower pitch. When the wavelength increases, this is known as a redshift. Okay, let's summarize then what we did right in this video. For a stationary source, right, the waves spread out equally in all directions, and the wavelength does not change. When a source is moving relative to an observer, not only does the intensity change, how loud the sound is, right, changes, but also we perceive the frequency to change. How does it change? Well, if the source of the sound waves is moving towards the observer, the frequency is perceived to be higher, right? Higher frequency means the wavelength is shortening. This is known, right? A shortening of the wavelength is also known as a blue shift. Moving away from the observer, right? The source is moving away from the observer, the frequency is observed to decrease. And at the same time, the wavelength will perceive to be, or will be perceived to be, become longer, right? Wavelengths appearing longer is also known as a redshift.